Hello, my name is Behram Mohammadi. I'm a PhD candidate at Carnegie Mellon University, Tepper School of Business. In this video, I'm going to walk you through my job market papers, and in a future video, I will get into more details about the findings and the methods that I introduced. Without further ado, let's get to it. So, as you can see, it's two essays on large language models in marketing applications. Right off the bat, I should address the elephant in the room. Why are there two papers in my job market package instead of one? Well, I should say that I do have experience of writing long papers. My first paper in marketing was about explainable AI. It was a game theory paper, and the entire paper with its appendix was maybe 80 to 90 pages long. So I have no problem with long papers. But as I was going through this project, I realized different parts of it deserve to be its own paper. So this is really two parts of one project that I just split in two papers. And the project is about studying the behavior of simulated AI agents in marketing applications. You can see the first paper addresses something of this project. It's about token noise, and the second paper addresses another aspect of this project, which is about the creativity of these agents. And so the project itself you can think of as like psychology of AI. But I also understand that simulated AI agents is a mouthful, and I better let you know what I mean by that. And I think the best way is to demonstrate it to you. So here's an app. This is a real website that I created last year when I was a TA for a course at Carnegie Mellon. And in this course, we wanted to move from traditional case studies that students usually have to analyze in business schools to something more interactive, something that students could talk to and get feedback. And in order to do that, we thought, what if students would interact with the agents in the case study? So here, for example, I created an app, and I created an agent called JD, because we wanted names to be anonymous. And this is supposed to be an employee, and students would have to interact with this employee, or synthetic employee, should I say. And they would have to learn how to apply the course concepts in sort of a real-life experience or scenario. So here you see that I'm interacting with JD, and she's not performing well, and I have to give her the bad news about the fact that she's not getting the promotion she wanted. So I'm going to just play a short part of it, the way she starts responding to my questions.
Certainly, I understand the importance of my role in ensuring team performance and project momentum. It's been challenging to maintain a consistent workflow with the ebb and flow of urgency from leadership, coupled with projects that sometimes stall or are shelved without clear communication.
All right. So this is JD talking about her role, and I can see that she is burnt out. I can tell because she sounds like a PhD student. Well, anyway, but you can see that if we were able to simulate these kinds of agents in different scenarios, it would be really useful for marketing. There's already some startups that have started to create these synthetic customers for firms so that they can run some research on them. For example, if you are able to replace some of these human subjects in marketing research studies with sort of AI agents, assuming that those agents can sort of reflect the preferences or cognitive biases and behavior of real humans, then it would be huge. You would be able to save on costs and also the time of running your marketing study. And you could iterate over different kinds of new product attributes. So it's great. Obviously, there's a lot of temptation. There's a lot of incentive to go ahead and do this in practice. There's also the possibility of using these agents to train your workforce. For instance, let's say you have customer support that now needs to be trained to be able to interact with different kinds of customers. Maybe some of them are angry, some of them are going to be nitpicky, and they're going to have different kinds of preferences for the product, different behavior. and your customer support needs to be able to address all of them. So of course, you don't want to risk it on real customers, so you can train your workforce on these simulated customers. If you're interested in behavioral research also, there's a lot of possibilities. If these AI agents are going to behave like humans, you can, for instance, run some preliminary research on them, and maybe you find some signs of an effect, and then you go ahead and run your research on the actual human beings. And there's also the fact that some kinds of research is just, illegal or unethical to run. So for instance, if you want to find the effect of something in like job advertisements, and you want to just show it to people of a certain ethnicity, you know that in many locations it's actually illegal to basically just show some job advertisement to certain groups or demographics. But if you want to find out how that's going to affect those groups, then you can maybe use these simulated AI agents to see what the response is going to be like. And behind the scenes, all of these agents that I said are actually very simple to create. On the right, you see some text that we call persona that we give to the large language model that's going to simulate an agent. In this text, we're going to give it like some instructions on like how to interact with the user, like what are its demographics, what are its background stories, and things like that. The text is not supposed to be that readable, that's why it's small. But really what we call this process, we call it priming the language model. And usually larger models are better at following these kinds of instructions. So the language model sees this thing that we call system prompt, this priming, and also the user's query. In this case, the user is going to ask something from the synthetic agent. But the user doesn't see this like prompt or this persona that we gave to the model. As far as they're concerned, they're interacting with something that's simulating a customer or employee or job applicant, things like that. But you see, with this simple setup, we can ask interesting questions. First of all, when interacting with these agents, the question is, to what extent can we expect them to replicate actual real-world human behavior? There's an old saying that says, if it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck. And that's called abductive reasoning, for good reasons. But so we can change it to say, if it writes like a human, reads like a human, and responds like a human, is it probably a human? Can it replace a human subject in a research study? So that's an interesting question in and of itself. But we also want to know, how do we create many of these? Because the text, the blue text that I showed you, was already a long text. And you can only imagine if we are going to create like thousands of different customers or these simulated agents, we cannot do this manually. So one idea is to use another large language model to create these personas for us. So the question is it even a viable solution? Like, what are some of the like pitfalls of using that approach? So together, these two questions are answered in the papers that I'm going to present here. So the first paper, Wait, It's All Token Noise, Always Has Been, Interpreting LLM Behavior Using Shapley Value. Let me start by saying something that we probably have seen before. There's two views on LLM applicability in marketing research. Some papers or some startup articles or like results that people have shown to like other people claim that LLMs cannot simulate real-world human behavior. Let's say you are interested in some behavior such as risk aversion, and like so this axis is like the values of risk aversion. Let's say you have some prospect theory model, and there's like a lambda for risk aversion, and you see that the distribution of that value in the real population of humans is this blue curve. But then if you go ahead and ask those questions from LLMs to measure their risk aversion, you see that their curve looks like this. So a group of papers argue that because of this like gap between the behavior of LLMs and humans, then we cannot use them in marketing research studies because they just don't behave like humans. But we also have evidence to support that we can simulate real-world human behavior using large language models. There is like a group of papers that argue that, hey, we went ahead and let's say we showed that the coefficients of a utility function derived from a conjoint analysis run on LLMs are very similar to the coefficients of a utility function of a conjoint analysis run on actual human beings. That was a long sentence. But really what it's saying is that some research suggests that the behavior of LLMs and humans cannot be that far off from each other. It can actually be very similar. But if you're looking at these two findings or groups of findings, then really the question that we start to ask ourselves is, what aspects of the research or the prompt that these researchers use cause the language model to go ahead and maybe sometimes behave like humans and sometimes not behave like humans? So we do need some explainability method, again, XAI comes here, that can explain the output of the LLM. And for what it's worth, we want this XAI method to be model agnostic. We want to be able to apply it to like ChatGPT, Claude, open source, closed source, proprietary. We don't care what model we're using. We want to be able to use some interpretability method that tells us what aspects of the prompt are driving the language model's decision and to what extent. So if there were an Olympics of language models, we want the method to be applicable to all of them. So such a method, we also want to have grounded in solid theoretical foundations. Instead of like using our own intuition or subjective design decisions, we want some like theory and some math to determine how this method and how these values are going to be obtained. And because of this theoretical foundation, this method, it would be nice if it had some guarantees about some like certain sensible properties. So, what they say is like a picture is worth 1,000 words. I'm going to show you 1,000 pictures that are worth an equation. And this way, I'm going to build up intuition for the Shapley value method that I am proposing to use in this paper. So let's say we have a prompt like this. The following flights are available from City 1 to City 2. Which one would you choose? Flight A costs $400, travel time is 7 hours. Flight B costs $600, travel time is 5 hours. So let's say we have this prompt and we ask it from a language model. And the language model actually gives us choice probabilities, like the probability of choosing token A versus B. If we go ahead and look at that, maybe 84% of the time, the language model chooses flight A in this scenario, and 16% of the time it chooses flight B. Okay. So now we would like to take this prompt and say, what is the contribution of this word flights, as an example, to that output that we just saw? So for example, that 84%, how much of it was because the word flights was used in the prompt? Okay, so Shapley value tells us, okay, go ahead and choose a setup, which I will define it more rigorously later. Choose a setup where some of these tokens are absent. So here we have like some tokens that we see like underscore here. These are absent in the prompt. If you go ahead and ask this prompt from the language model, the choice probabilities, let's say, look like this. So A and B, almost 60-40%. But now we're going to inject the word flights that we were interested in to this prompt. And we're going to ask the prompt again from the language model. And now we see that the choice probabilities change. Okay, so from here to this. So we record the marginal contribution of the word flights to the setup SK, and we move on. Then we consider another setup. In this setup, only 2 words are absent. And flights is one of them, obviously. So if we go ahead and ask this from the language model with almost 80% probability, it chooses A, and 20% B. Again, we're going to add the word flights to this prompt, and now the choice probabilities change like this. Again, we record the marginal contribution of flights to this setup. In general, these setups we call coalitions, and this word flight that I just said, they're called players. So in cooperative game theory jargon, we assume that all these tokens that we see in the prompt are like players in a game, and they're all playing to get some overall output, which is the output of the model, the 84% versus 16%. But when we look at the output of the model, of course, the model looked at all of the tokens, but it didn't look at all of them equally. So some of the tokens played a much more important role in the decision of the model. So that's why we call them like players, and like these are called coalitions. We repeat this process for all possible coalitions. Each time we record the marginal contribution of flights, or the player that we're interested in, to the LLM's choice probability of A for that coalition. And so we get like a total marginal contribution, and we do a weighted average of the marginal contributions over the possible different permutations in which the coalition can be formed. And that gives us the Shapley value of the word flights. We can obviously do that for all of the tokens in the prompt, and we end up with a vector of Shapley values for all of the prompt tokens. So mathematically, this Shapley value that we see here, the purple one, is the average 1 over I factorial, and I is the number of players, of player I's contribution, which we show like this. The contribution is using a set function called V, which is the value function. It tells us what is the output without adding player I to the coalition and after adding player I to the coalition, okay? And then to each coalition S, that doesn't include player I, weighted by the number of permutations in which the coalition can be formed. So you can think of this blue part as, let's say, there's a coalition with cardinal of S members, right? With cardinal of S factorial different ways, those previous tokens could have been added to that coalition, right? And then you add the current token, and then after that, whatever number of tokens left is the total number of players minus the coalition minus 1 that we just added. And again, we take the factorial of that. When we multiply them, it's like when we add the word flights, before and after it, different players could be added in many different ways, in many different orders. We basically, that will give us the multiplier, that will give us the weight that we assign to the marginal contribution of the word flights to that coalition. And there are alternative formulations for Shapley value, and in a future video I will get into more details of this. But suffice it to say that in practice, calculating Shapley value is computationally infeasible. So let's just take a look at this one, I factorial. I is the number of players. If you have a prompt with like 128 tokens, you have to calculate 128 factorial, which is not computationally feasible. So that's why we need to use a Monte Carlo simulation, which I introduced in the paper, to estimate the Shapley value. Mind you, the Shapley value doesn't care about the underlying transformer architecture. The Shapley value method tells us, as long as you give me the choice probabilities of each token when the language model generates them, then I can give you the Shapley values for the tokens in the prompt. So the Shapley value method is not concerned with like hundreds or like thousands dimensional space of the embeddings of tokens in the language model. It doesn't care about the underlying architecture. It could be transformers, could be Mamba, it could be something else. As long as it gives us choice log probabilities for the tokens, we can apply the Shapley value method on them. And it gives us some interesting mathematical properties. For example, efficiency tells us that no amount of payoff is going to be missed or lost during this process of distributing Shapley value on the players. Symmetry tells us if two tokens or two players contribute equally in every coalition, then they should receive the same payoff. the same Shapley value. Linearity and dummy player are also interesting properties. So if you have two independent games and one of them has like value function v and w respectively, then each player's payoff should be the sum of their payoff in each game. And of course, finally, a player who doesn't add any value to the collisions should receive no payoff. So let's go ahead to summarize. In a nutshell, the method that I propose in this paper says, let's go ahead and treat every part of the prompt as players in a cooperative game, and then the reward would be the choice probability of the model for like flight A, and then calculate the Shapley value for each player to find their share of the payoff. So if we have this, let's go ahead and have a look at some of the examples that we can, some of the example outputs of the Shapley value method. Again, going back to the prompt that I showed earlier, let's go ahead and look at some intuitive graph. Like if you were to choose between these two flights, you probably pay a lot of attention to the price and travel time, and the fact that the travel time is expressed in hours, so the unit is hours. And similarly for flight B, you look at the price of it and its travel time. So intuitively, we expect to see like higher Shapley values for these tokens that carry a lot of information about the flights. And we expect to see like smaller amounts of Shapley value for other tokens, because they don't really determine the description of the flight. They're like mostly parts of speech, right? But in reality, what we see is something like this. So let that sink in. First of all, the language model is smart enough to pay attention to the second part of the prompt that actually contains information about the flight. So that's good. But we also see abnormalities like this. So the word "the" at the beginning of the prompt was as important as the price of flight B. And we also see similar patterns going on here, like some of the tokens that should not really be that important when the model wants to choose between A or B are actually really important. Like the word is actually more important than the price of flight B. And we also see some really high peaks of the word flight, flights, and flights. We can use this to sort of change the output of the language model, because if we look at the Shapley value insights, we can say, okay, I'm going to drop the word is, I'm going to change the word flight to option and flights to options. Okay, so semantically the prompt is the same. So if you ask this prompt from another person, it like really shouldn't make a difference. But we see that the choice probability of B more than doubles. Now imagine this. Let's say you show that a conjoint analysis can be run using large language models. A conjoint analysis gives us coefficients for the utility function. Those coefficients depend on the choice probabilities of the respondents when they see questions like this. Now, what happens if those choice probabilities are too noisy? Then the coefficients will be noisy. So essentially, this paper tells us that you cannot really reliably expect the language model to behave like humans in every scenario. Even if the choice probability on the left is similar to human behavior, there is no guarantee that in practice, firms, when they use their own prompt, they will not get something like this. There is no guarantee that the language model will still behave like humans. So it's like we have gone from p-hacking to prompt hacking. You can basically change the prompt as much as you want until you get the choice probabilities that you want. But it's also another concern for behavioral marketers too. Behavioral marketers have been using a lot of techniques over the last few decades to study different cognitive biases or patterns of human behavior. One of them is framing effect. I have chosen it for its simplicity. Framing effect is essentially when you express one option more positively than the other one, then humans are more likely to choose that. if we go ahead and try that on a language model, we see, for example, the following flights are available, blah, 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 blah. And if we add a positive framing phrase like only, then we see the choice probabilities are now in favor of flight B, because flight B costs only $600, okay? And on the surface, we should be happy because the language model seems to show signs of being vulnerable to cognitive biases, at least the framing effect. But remember, we also saw the effect of tokens. We also saw that the decision of the language model could be driven by tokens that should not really be that important. And indeed, when we look at the Shapley values again, we see that the effect of token nodes still exists in this prompt. Although we do see the language model pays attention to the word only, still some other tokens are driving its decision more. So we can again use this to go ahead and do this. We're going to replace the word flight with option. Instead of saying something costs $400, we say something priced at $400. And that's it. Just few subtle changes to the prompt. And we still keep the word only here, by the way. But we see that the effect of framing effect disappeared. So before, we were able to make the language model choose flight B much more than before, but now the effect disappeared. So what does it mean? Going back to the two views that I mentioned on LLM applicability. This paper says both camps in the literature are right. Depending on the exact wording of the prompts that they use, both camps are right, both papers are correct. But we need to start looking at large language models the way they are. They are generative models. They are generative in the sense that they receive an input, which is the prompt, and then they generate something. And this something is a distribution. Okay? So essentially, a large language model is not one entity whose behavior or preferences we want to reveal, you know, like as a curve that I showed before. It's a distribution of distributions. Just like, you know, people who are familiar with Bayesian statistics, you know, when we look at Dirichlet data generating processes, it's something that when you sample from it, it basically generates Dirichlet or beta distributions. And these graphs, by the way, are actual graphs from the Shapley value method. As we distort the prompt, we go from distributions that highly favor choosing flight A to distributions that highly favor flight B. And for those who are familiar with beta distributions, you can fit a beta on this and find out the parameters, the alpha and beta parameters of this beta. But essentially, the paper tells us that the very act of measurement changes the preferences of the model. Because remember, we calculated Shapley values for questions. So depending on how you ask a question, the language model's response would be different. And this is something that's similar to the uncertainty principle in quantum physics, where the very act of measuring something changes it. I don't want to get into that in much detail, but like the fact that you cannot find the location and momentum of electrons in atoms at the same time, that's because of the uncertainty principle. And similarly, we have a similar concept here that you cannot really measure what's the preference of the language model for something, because when you ask it, you change that preference. So let's go ahead to the second paper. Creativity has left the chat, the price of debiasing language models. All right. For this, I'm going to start by talking about some series of steps that firms usually take when they're training large language models. The first is pre-trained or base model. You train a transformer on a large data set, and what you get is like a base pre-trained model. It's not that useful. It's like a fancy autocomplete. Then, of course, you fine-tune it on some data set. It doesn't have to be that large, but you fine-tune it on prompts and responses, and these prompts and responses usually look like questions and answers. And the language model starts to understand, oh, okay, when I see a question, I need to answer it. Okay, this is what we call an instruct or chat model. And finally, the companies usually run this RLHF, or reinforcement learning from human feedback process, on the language model. And this allows the model to avoid writing toxic or biased content. So it learns that if it writes certain kinds of content, it's going to get a lot of penalty. And instead, if it writes other kinds of content, it gets rewards. So I'm going to actually show you an example of what I mean by these things. And I think I better use an example like this. So here, I'm going to enable both models. The base model that was not gone through like instruct, fine-tuning, or RLHF, and also the instruct model. So if I go ahead and ask this question from both models, we see that the instruct model answers my question. In this case, I asked it to create a customer profile with the following attributes: name, last name, education level, nationality, gender. And the instruct model followed my request, but the base model just continued asking another question. It doesn't have a concept of like answering questions. If I repeat that again, we see that it's just like creating nonsense at this point. So what really is going on is that we need instruct models, we need chat models because they're useful, but unfortunately, this RLHF process that's applied in the end, that causes problems for creative professionals. I'm not going to talk about the details of the RLHF process here. That's going to wait for the next video. But I want to mention just at a high level, LLMs produce one token at a time, right? A token is roughly 3/4 of a word, but bear with me, I'm showing like words here, not tokens, for simplicity. So LLMs assign logits to every token that they have in their dictionary at every step. And like it could be like 128,000 tokens or 30,000, depending on the model you use. And so the model assigns probabilities or logits to the tokens. In this case, I'm just showing 3 tokens at each iteration. And then it samples from them according to their probability. So sometimes the one with the highest probability gets chosen, like this one. Sometimes the one with like lower probability. But in the end, what you get from the model, the text that you get from the model, is really token trajectory. So the first token comes from this, then the second token comes from this, and the third, and so on and so forth. So you can think that if the model responds to you at like 100 tokens, it's like a deeply nested graph like this. It's like token trajectory. Now, remember that. I'll get back to this. Let's ask a question from a language model. Let's ask it to create a customer persona for us. But in this case, we're also going to ask it to write a review for a product according to each customer that it generated. Okay? So the customers should have first name, last name, gender, nationality, ethnicity, and also personality type according to the MBTI test. And the product that these simulated agents are going to review is a coffee machine that connects to your smartwatch so it keeps your coffee warm if you're far away from it. All the more reason to get good jobs and be able to afford such a coffee machine. So if we go ahead and ask it from the base model that did not go through the RLHF process and the align model that did go through the RLHF process, we see some discrepancy. The base model is able to generate all kinds of names and last names here, whereas the align model really likes certain names. I'm pausing here because it is actually surprising, because this has nothing to do with like toxic content generation or like bias or anything. It's just the model was asked to create customers, and the names it came up with are really like concentrated on certain names. It cannot generate all kinds of names. And the same also applies to nationalities. The base model was creating customers that came from all kinds of countries, whereas the align model learned that certain few countries are just exist. Like it doesn't even choose any other country. When we go ahead to ethnicity, we see that the base model was able to choose all kinds of ethnicities, whereas the align model chooses fewer of them. Now, I should mention that the point of this paper is not to look at the distribution of each of these attributes. I'm not trying to make a case for or against like models bias in terms of like, for example, ethnicity bias. My point is actually that just the number of different ethnicities that the model even considers, okay? And it seems like that the aligned model doesn't even consider many of the other attributes, many of the other values that this ethnicity can have. And personality type is an interesting one because we have like 16 different personality types according to the MBTI test. And the base model covers all of them, whereas the aligned model just doesn't even know that 10 other personality types exist. And the distribution of age is an interesting one too, because we see the Gaussian distribution with the base model, whereas the aligned model just doesn't know any concept of like the age 33, 34. It just really likes age 32, which just so happens to be my age. But yeah, it doesn't generate customers of different age groups. And also for gender, we see that the previous model, the base model, was, biased towards males, but it still generated female customers, whereas the aligned model almost always generates female customers. And this one is a little bit funny because when we look at the length of the reviews that these simulated customers write for the product, we see there is a significant difference between the length of the reviews of base and aligned model. It seems like during the RLHF process, the aligned model learned that the more it talks, the more reward it gets. So it just talks more about the product for some reason. And also it learned to always be positive. Like you look at the sentiment of the reviews generated by these models, you see that the base model can create all kinds of sentiments, even negative ones, whereas the aligned model almost always just says positive things about the coffee machine. So this is like already concerning because as a marketer, you want to, let's say, create different kinds of synthetic customer reviews or product descriptions, or maybe you want to do ad copywriting. You want as much creativity as possible. You don't want the model to just stick to certain words or phrases. You want the model to just say all kinds of things. And unfortunately, the aligned models do not have that capability. Well, maybe the task was tough, right? Maybe we were just asking too much. We asked it to come up with like hypothetical customers, and maybe that was just like challenging for the model. So in this second experiment, we're going to look at information elicitation. So we know Grace Hopper was a computer scientist who created the COBOL programming language that's used by many financial firms and banks. And we know that both models, the base model and the aligned model, have the same knowledge about Grace Hopper. They were trained on the same data set. So what we're going to do is we're going to give this prompt to the models and we just let them roll. We want to see how they complete this sentence, okay? So what really happens is that on the left you see the base model output, some samples, and on the right you see aligned model output. And we see that the aligned model seems to just generate some like repetitive paragraphs about Grace Hopper. And actually we can see that in these graphs that we have here. On the left you see the embeddings of the paragraphs generated by the base model, okay? So embeddings, we use the sentence BERT algorithm to go ahead and find the embedding of each paragraph generated by the model. And then we use the TSNE algorithm to reduce the dimensionality to 2 so we can visualize it. So on the left, you see that in the embedding space, the base model is able to create all kinds of embeddings, all kinds of different meanings of paragraphs about Grace Hopper. Whereas on the right-hand side, we see that the aligned model can only explain or describe Grace Hopper in 4 major ways. It seems like something's missing. It just lost its ability to create some semantics, some meanings. So something is going on, and this is where we get a little bit philosophical. Let's think about it. We notice that syntactic diversity is a necessary condition for semantic diversity. By syntactic diversity, I mean like the words and tokens that the model can choose. And semantic diversity is the meanings that it can produce. So Essentially, if you just give me the word hello, I cannot produce the meaning that something that means goodbye. I should have access to all the words in the dictionary so I can generate all kinds of meanings. And the hypothesis here is that when we observe low semantic diversity, as in the Align model when it described Grace Hopper or when it created all these customers for us, it is because it has low syntactic diversity. So the root cause of the problem, the thing that RLHF does to the model, is that it blocks certain token paths or trajectories. So at each step of token generation, the model doesn't have access to the full dictionary of tokens. It actually has access to few tokens at a time. And that's why no matter how many times you ask the model to generate an output for you, it will generate repetitive output over and over. So going back to the graph that I showed before, imagine some of these paths are blocked by RLHF. So because of that, the LLM fundamentally loses the ability to write syntactically and semantically diverse outputs, even at high temperatures. By the way, in all the experiments in this paper, the temperature is 1, which is the maximum that we can use. So let's go ahead and test this syntactic diversity hypothesis. Here we have another prompt. Steve is the CEO of a startup. And here we're not going to look at the embeddings now. We're going to look at the exact tokens that the model generates. Okay? So the idea is that if you have high syntactic diversity, then it arises when the probability distributions for the tokens that are generated by the model are more spread out, and vice versa. So actually, this is what happens. When we look at the generations of the base and align model, when they complete our prompt, we see that the base model sort of spreads out these probabilities among many different tokens. Here I'm just showing the top 5, but really, for example, look at the first one. It is assigning non-zero probability to several tokens. So every time you sample from it, it is possible that it will generate something else. And at each point in the token generation, the model could go off to a completely different trajectory because it is able to generate different tokens. So for instance, Steve is a CEO of a startup company 4 years in. He is looking for a financial partner, or maybe could say a financial advisor, a financial investor, a financial analyst, things like that. And by choosing each of these tokens, the model will be generating a completely different output. So the base model has the privilege of choosing different tokens, whereas if we look at the align model, we see these are actually much more concentrated around certain tokens. So at each step of the way, the model is not likely to generate different outputs because some tokens just get all of the probability. Like look at this one, the team, or just the word D, A, of. So it's like one model can create multiverse for us, like all kinds of possible outcomes that can follow from our prompt. And one model can generate universe for us, like the align model. And we can see that by looking at the entropies of these tokens. So for example, on the left, we see that the model feels hot, the same way that hot objects have high entropy. And on the right-hand side, we see that the entropy of the model has dropped significantly. Essentially, we went from a hot model to a cold model. It cannot generate all kinds of outputs. And this is why the alignment process reduces the creativity of the model. It blocks certain paths in the token generation process. And why it happens is something that I explained in the paper. It has to do with the PPO algorithm that's used in reinforcement learning. And in a future video, I will get into more detail about that. So, but let's take a look at the clusters we saw earlier. These actually have an interesting property. These are not just typical clusters. Let's go ahead and do something fun with them. Let's perturb the trajectory that the model would generate in each of these clusters. So let's say we had the initial prompt was Grace Hopper was, and the model generated this paragraph. You see that green shows most tokens were like with probability almost 1, and like red and orange and yellow are like less than 1 probabilities. And so like you see, the model generated this, and it belongs to I think this cluster. So now what we're going to do is we're going to take this, the first part of this generated output, but instead of saying she was, we're going to say she was not. So the model didn't expect to say she was not. Okay, in all of its generations, it would choose she was and then continue its generation from that. But now we're going to take the model out of distribution. Okay, so now the new prompt is Grace Hopper was born on November 9, 1906 in New York City. She was not. And now the model has to continue this prompt. And we see that the model first gets confused because it was not expecting to see not. It's out of distribution. We see that it struggles to justify it. First, like the first few tokens are not green, even though like they used to be like before. So the model tries to justify this. It says she was not 9, she was actually 114 years old when she passed away. And then something weird happens. The model goes on to generate its own output as if nothing happened. So you see here it's going to say Grace Hopper was an American computer scientist, which is one of the typical cluster outputs that the model generates. So it's as if when you nudge the model out of one of these clusters, it just gracefully, pun intended, finds its way back to the cluster. In dynamical systems, they call these things attractor states, sort of like black holes in space that attract the masses around them. And so this is concerning because it means the model has already made up its mind about what it's going to say. And even if you perturb its output a little bit, even if you push it out of its distribution a little bit, it doesn't matter. The model tries to justify that and find its way to its own in-distribution output. So is there a solution to this problem? Yes, there is. There is a subsequent paper, I will put it on archive in a few weeks, that modifies the underlying transformer architecture to increase the creativity of the models, even if they have gone through the RLHF process. And I have not included it in my job market package because it would make it too long. But in the meantime, what the results of this paper mean for us is that when you're going to need creativity, just stick to base models, and when you need consistency, stick to aligned models. So for instance, if you want to create different kinds of personas for like a simulated experiment, you go ahead and use base models like Llama 3, and when you want the users to actually interact with those, you go ahead and use aligned models such as ChatGPT or Claude and other models. And because they act more agentic, they act more like they know the concept of conversations. So now we come to the end of the presentation. This is, like I said, an overall big picture idea. And in the future video, I will get into more details. I hope you like this video, and if you have any questions or comments, feel free to comment down below. Thank you so much.